Hi everyone, and welcome back to the Information Bottleneck. And today we are going to talk about text diffusion models. And for that, we have Brendan Odengo. He is a director of research at Google DeepMind. Hey Brendan, thank you
Hi,
for joining
guys.
us.
Hi. Thanks for having me. I'm excited to be here.
And also we have Ellen. Hey Ellen.
Hi, Ravid. Hi, Brendan. It's good to be here.
So today we are going to talk about text diffusion models. So Brendan, maybe you can start and tell us a bit what does it mean text diffusion models and how it's different from the regular autoregressive one.
Sure. So let's start with just diffusion models in general. So diffusion models are a type of generative model where you learn, the model learns to map a distribution that's easy to sample from to the target distribution that you want to draw samples from via this kind of iterative process of denoising. And diffusion models are state of the art for image modeling, video modeling, protein modeling, a bunch of stuff. And the way they are trained is you take the ground truth data that you want to model and you add some noise to it. And in the continuous domain, that's typically Gaussian, but it doesn't have to be. And then you train the model to the neural network to remove that noise. And then there's various ways you can do that, but typically you try to just get back to your original data that you started with, given the input being the noisy sample. And then you train it on a bunch of different noise amounts and a bunch of different data. And then when it comes to inference time and you want to sample from the data distribution that you care about, you just give the model pure noise, so pure Gaussian in the case of Gaussian diffusion. And then you iteratively apply the neural network and kind of move along this kind of ODE flow of this kind of probability density towards maximizing the data distribution that you care about, so you can draw a sample from the data that you care about. So that's kind of diffusion at a high level. And then text diffusion is the same idea, just applied specifically to the data being text. And you can do that in a variety of different ways. You can do that continuously, just like for images. But I think state of the art right now, at least, is to do it using discrete diffusion, which is kind of slightly different setup and a bit different math from the continuous diffusion cases, but it's kind of a similar high level idea where you start with the clean discrete data, which is in our case text, and then you corrupt it by adding noisy text into the text sequence that you want to model. So you kind of corrupt the sequence that you're trying to learn by injecting random tokens taken from the vocabulary, so-called multinomial diffusion, from a paper from Emil from I think 2021 or something like that. You just corrupt it with random tokens from your data, so it just looks like a noisy kind of gibberish string at different noise levels. So sometimes it's a little bit gibberish, sometimes it's like totally gibberish, and you train the model kind of like BERT to fill in the correct information given this kind of corrupted sequence. So try to fill in the ground truth data that it was corrupted from. And then when it comes to inference, you start off with just pure tokens generated from your samples from your vocabulary, so pure gibberish. And then you iteratively sample from the model to fill that in with clean text, like that's drawn from your data distribution that's kind of relevant for your prompt or something like that. So that's kind of how the generative model works for discrete diffusion. And how it's different from autoregressive models. Well, so autoregressive models, they're kind of state of the art still for language modeling. So ChatGPT, Gemini, Claude, they're all autoregressive models. And the way they work is they basically trained to do next token prediction. And, you have this clean factorization of the distribution into a sequence of, predict the next token given the prefix. And then it's just trained in that way to just given a big long sequence, you do causal masking inside the transformer and you can predict the next token. And then you just train it on a bunch of data and you can then sample from it by sampling one token at a time. Whereas in diffusion, you still have some context, like some prefix that you want the model to answer, but it's just a different way of generating text, which is you start with corrupted data and you iteratively refine it in this process. And that has a bunch of pros and cons relative to autoregressive models. But yeah, that's kind of the high level idea.
So maybe let's talk a bit in high level. So why did you bet on text diffusion? Right, autoregressive models were ringing everywhere, everything, right? So what convinced you that this worth a whole team?
Yeah, I think I started working on text fusion like 2023, like three and a bit years ago now. And kind of at the time, I thought that, diffusion was amazing and was producing such incredible like images and videos with like Dolly and stuff which was coming out at the time. it seemed like you autoregressive next token prediction is a really powerful technique for language modeling, but maybe that this other thing is even more powerful. Like it's just a way better way of generating every other modality of data except text. And it's just a matter of doing the work and getting the research done and finding the tricks that are needed to make the same technology work for text. And then it would be a massive breakthrough. And then it would be, it would replace autoregressive models entirely because it would be a better way to generate text. That was kind of like maybe naive in hindsight, but I think, I still think that text diffusion is the future in many ways. It has still, there's still a lot of open questions to answer. So it's not a solved problem in any sense, but I still think that we still don't fully know how to do it. And there's still some research needs to be done. And I'm still optimistic that one day it either will replace autoregressive modeling because it's a better way to generate text, or at least augment it, where it has these kind of niche use cases where you don't want to use an autoregressive model for whatever reason, you prefer to use a text diffusion model. I think we're getting to that world where these two models or modeling paradigms will exist in parallel.
So I have a few questions. I guess one is, I've heard others describe autoregressive text generation as a special case of diffusion. And so I guess your opinion on that kind of take. And then second of all, I've noticed that models that, at least today, I don't know if this is, and I guess my question is this just like a tendency of how the models are trained today or the data used today? Or is this an architectural thing around how, in general, at least for diffusion image models, they tend to be far more creative, which is to say like Stable Diffusion and all of its models don't have like a random orange tint on all of the generated images. But then autoregressive images have much better text encoders and thus much better instruction following. And that's been my experience there. I have not even used diffusion language models. So like, do you think that there's similar kind of tendencies? And if so, do you think it's architectural?
Yeah, that's a great question. So I'll try to answer the first one first, which is about the autoregressive and a kind of a special case of diffusion model. I think they are in kind of a limited, kind of not really insightful sense. So I think you can set up, you can write it down mathematically that, yeah, autoregressive models are a special case of like diffusion with one denoising step and a block size of 1 or something like that. So yes, it is, but I'm not sure if that really delivers any insight or it doesn't really prove that diffusion models are more powerful or anything like that. Yeah. So the second question, it has been my experience, and I think a lot of the people's experience, that diffusion models for language tend to be a lot more diverse in terms of their outputs than autoregressive models. And can generate, many, many, many different responses that are very qualitatively different for the same prompt. Whereas if you try to get diversity from an autoregressive model, you can, but it often kind of just rephrases itself in kind of not useful ways. And it's just been my experience that they tend to be less diverse, and maybe that translates into less creativity in some sense. Like if you kind of translate diversity of output into creativity. I didn't know that about the orange tint phenomenon. That's interesting to know. But yeah, I think it comes from the fact that diffusion models, when you sample from them, and also when you train them, but when you sample from them, you tend to kind of state-of-the-art methods, or like kind of predictor corrector methods or whatever, where you tend to inject a lot of noise back into the process. So you start off with all pure noise, and since you start off with a source of noise, that's already a source of diversity, because you can sample the initial noise in many different ways. And then as you're sampling, you do, let's say, 10 or 20 steps to generate 256 tokens. At every sampling step, there's the opportunity to re-inject noise. As far as I know, most of the state-of-the-art like samplers do re-inject noise, and that's another source of like entropy, and then the model will correct it in different ways for how the noise is added, either like positionally, like it'll choose different positions to add noise to, or like the actual tokens that get injected are different as well. And so that just ends up being that there's a lot more diversity and entropy in the final sample when you measure it versus autoregressive models. And this has a one concrete advantage over autoregressive models, which is in reinforcement learning, because in reinforcement learning, what you're trying to do is get the language model to produce many outputs for the same input, so that you can find one where it like got a high reward, or like, for instance, solve the problem, and then you kind of reward the model for that high rewarding sample, and you maybe you give a negative reward for something that did really badly or something like that, and then you kind of distill it back into the model via either policy gradient or something like that. And so what you want is, you want a lot of diversity in your outputs in order to make sure you can achieve kind of the high pass rate when you're given lots of samples. And it turns out, it's been my experience, and it's been like the empirical observation I have, that the autoregressive models kind of tap out at some number of samples that you draw. You need a lot of samples to get maybe a rewarding samples, but because language models tend to be so much more diverse, you can actually more likely to sample something that is totally different to another sample, and therefore get a rewarding, more likely to get a rewarding signal, and then more likely to be able to learn from that and kind of hill climb on these RL benchmarks. So I think it's a real phenomenon that just mostly from the sampling procedure, I think that these diffusion models, and my guess is it happens in image and video diffusion as well, that they tend to be much more diverse than autoregressive models.
And what's the best quality diffusion LLM today? And what's the delta between the best quality model and existing best LLM frontier models, in your opinion?
Yeah, and you need also to normalize to size and things like that, right? And data and
Yeah, so it's hard to know exactly. So we just released a Gemma diffusion model, which is an open weights model. That's a 26B, 3.8B MOE activated. And that's tuned for low latency applications, like to fit on a H100 and can hit more than 1,000 tokens a second and so on. And it gets reasonably close to the base Gemma 4 model equivalent that we started from. So I'd say that's probably close to state of the art or state of the art. The only other real contender that's close is the Mercury 2 model from Inception. It's also a very strong model. That's a closed API model, so we don't know how big it is. But from what I gather, it's a lot larger than our model, and it's served on B200s rather than H100. And it's a bit slower. It's about 500 tokens a second via the API. So it's hard to know, but it's probably between those two, and they tend to be pretty close in terms of the actual eval metrics. So it's probably between those two. But my guess is that both of those models are substantially smaller than the absolute frontier model, which, Claude or Gemini or ChatGPT or something like that, which are in the many trillions of parameters at this stage, from what I gather. And so it's hard to know exactly, if someone really did scale up a massive pre-train for a massive text diffusion model, if they could get close to the frontier or not. In terms of the gap, all I can tell you is that the gap from the Gemma model that we started from to the final one that we produced ended up being about 10%. And so there was a reduction in the quality when we took the autoregressive model and tail patched it or fine-tuned it to be a diffusion model. But that comes from a few different sources, and it's not clear that if we did the entire thing from scratch ourselves, whether or not there'd be much gap. My guess is it's pretty close to performance neutral if you trained it on the exact same tokens and so on. So
what do you think are the main challenges now to scale it to, 5 trillion parameters?
I think the main challenge probably is who's going to invest in that, and who's going to actually, pay for the compute in order to scale up to a 5 trillion parameter model. I think as a technology, the main drawback right now for diffusion models is, maybe quality is not quite there. It might be 2 or 3% lower. Latency is way better, so that's a big pro. It can be 4 to 8 times faster, something like that. It depends a little bit on the exact task that you're running it on, can be even faster. But the main disadvantage right now, and I know for a fact that this is why OpenAI are not investigating this direction, is because if you compare serving a text diffusion model to serving a very high performance, highly tuned autoregressive model, serving inference setup with that's receiving many queries, many thousands of queries a second, then you're going to need more chips to serve the same QPS from a text diffusion model, because the text diffusion model, you end up hitting a compute bound threshold earlier than an AR model. And so yeah.
I was just going to ask, related to that, when you said 500 tokens a second, were you talking prefill or decode, or is that still a coherent distinction with diffusion models?
It is a coherent distinction. Yeah, I'm talking about decode.
Okay.
Yeah.
Do you know what prefill is? I care now because agentic coding is such a big deal, right? And so prefill ends up becoming more and more. And
Prefill
then
will be much, much faster. Yeah, much faster. Like
okay, good.
many thousands of tokens a second in prefill. Yeah.
Okay. And then I guess my other question is, it seems like diffusion language models, I need to test them. It seems like they're a lot more diverse and creative by design, right? And indeed, I know that the whole theory of sampling with them is totally different. Like temperature becomes a computationally intensive is just one of the many changes that you have to think about. What I'm curious about is it seems like OpenAI and Anthropic also have reduced like control over sampling knobs and abilities basically to improve creativity, almost certainly from a alignment and safety angle, because it increases the risk of getting out of that kind of.
Right,
So
right.
do you think that diffusion models have fundamental problems with alignment and safety in this regard because they're so much more easy to get more creative outputs out of them?
Yeah, I mean, it's a good question. It's possible. Yeah, it's possible. I haven't really investigated that too much, but it if that's really the reason why Anthropic and OpenAI have turned off some of those knobs in order to prevent more diverse outputs, then obviously a more diverse technology would be something similar. I guess the only data point I have really is that we were our diffusion gem model, we had to make sure it satisfies a bunch of safety benchmarks, which we were able to do. It was a bit more challenging than the autoregressive model to get those safety benchmarks. So that is a potential source of why maybe it was harder to get those safety evals. But since we've released it, I don't think it's been obliterated, which is this thing where people are able to fine tune away the safety guardrails that we train into the model. At least last time I checked, which was maybe a couple of weeks ago now, no one had managed to fine tune out the guardrails that we put in. So maybe there's something different fundamentally about the text fusion that makes it harder to fine tune out the guardrails, or maybe just it's been less investment and people don't know how to do it as well yet.
It's funny you mentioned this. I work with the Heretic creator.
Oh, okay, yeah.
So now that you mentioned it, I'm sure he's probably listening. It's like, oh, I'm going to check that out.
Oh, well, that's good. Go ahead, please do, and write a paper how you did it. Yeah. I mean, for the sake of the community, I'd love to know how to do it. So please, obliterate it and then write a paper and tell us how you did it, and that'd be fascinating for us who work on that.
But what do you think are the domains or the use cases that you believe actually text diffusion will be better than autoregressive?
There's a few. Yeah, it's a good question. So right now, I think as the technology as it is, there are a few cases where it's already better. The obvious one is low latency applications. So anything you need a latency constraint, it's just you're going to hit that latency constraint much easier than with a text fusion model than with an autoregressive model, because they are many factors, 4 to 8 to 10 times faster, even including state of the art speculative decoding techniques. So that's relative to the state of the art, MTP heads and so on. So in low latency applications, and then on device use cases. So we have some that we've actually deployed text fusion models into on-device products within Google, mostly because of latency requirements. So you could imagine things like robotics, where you want you want a on-device model on your robot to do planning or action control or whatever it might be, and you want that to operate as quickly as it can in the real world and to react to things that are happening as fast as possible. And so you want a low latency device on your robot. Same with a self-driving car, very similar, driving down the freeway at 70 miles an hour. If there's an LLM in there, then you want that to react as quickly as possible and to be able to hit the latency requirements. On device on a phone as well. So we have some work with the Android team potentially investigating putting a text fusion model onto the phone in order to basically give them a better user experience, because you can talk to your phone or you can get your phone to do some task, and it will, if it's actually running on the phone, it'll respond a lot quicker. It'll be a better user experience, and also uses less battery, it turns out, because even the text fusion model, text fusion in general, because it's so much lower latency, it activates TPU or the accelerator chip that's on phones less. And then when the GPU is activated less, it's not drawing current when it's not on. And so it actually drains the battery less. So both in terms of power consumption and latency. And so overall, much better user experience when it's on a phone. So I think right now, the use cases are low latency applications, on-device applications, and then there's some benefit as well, which we have empirical evidence for the bidirectional nature of the way that the text fusion model can reason and attend to the future and so on. Now, there aren't a huge amount of applications of this that we've been able to find, but for instance, Sudoku, which obviously nobody really cares about, in practice. But the text diffusion models are just way better at Sudoku because they can fill in at any point in the Sudoku rather than having to be restricted to some particular order. So if there's any problem like that arises, then there's an advantage to being able to do bidirectional reasoning and to do or any order fill in. So I think those are the use cases right now.
And what do you think about like combining autoregressive and like text diffusion? For example, these days people are using like parallel drafter, right, in speculative decoding. That this is kind of like diffusion style models, right? That like you have the drafter, like a small drafter that you can generate like the tokens in parallel. So do you think this is something like do you think about these directions, or do you think like it's like the two different distinct
No, definitely. I
form?
think that's a very important direction. And the diffusion Gemma model that we released, we didn't highlight this at release time, but it's going to be in the tech report that we're putting out in a few days, is able to do both modalities. We specifically trained it to be both an autoregressive model and a text diffusion model. So people could play with that and see if there was any interesting use cases. In the autoregressive model, it's close. It loses a few percent of points relative to the AR model we started from, which is the Gemma 4 like 26B model. So it's a little bit worse than that, but the fact that it can do both modalities, so you can do generation in autoregressive mode or in text diffusion mode, and you can also do scoring in autoregressive mode, because that's like an advantage to have, which is to have exact likelihoods under the model distribution, like the AR mode. I think there are use cases for that. Like some people internally have played with things like, these reasoning models, they can spend ages reasoning, and that can add up, eat into your latency a lot. So you could imagine. But you don't need to do perfect reasoning. It doesn't have to be like really high quality reasoning. You kind of just need a coarse reasoning. So you could imagine, and some people have played with this, you could imagine having the text diffusion model, which is able to run in both modes, do all of its thinking, like all of its reasoning in a text diffusion mode to try to get it done as quickly as possible and really lean into the low latency aspect. And then when it comes to actually responding and like, let's say writing the code or whatever you need to do, and you want that to be very precise, and you don't mind waiting for that because the expensive part in terms of wall clock time is done, you switch over to autoregressive mode, and then it just does one token at a time. It's slower, but it tends to be like slightly higher quality. And then combining those two modes, I think, could be very powerful going forward.
So with these diffusion models, I know at least from the image generation space that there's a vibrant ecosystem of the equivalent to like LLM autoregressive samplers, which are known as SDE solvers, right? So you've probably heard of these Euler, DAP, DP, etc.
Right.
I don't know anything really about how they interact with the diffusion LLM ecosystem. I'd love for you to say anything you know about this. And I've one thing I do have heard is that despite there being many, second or third derivative based methods, which are much more computationally expensive and in theory supposed to be more accurate, in practice it seems to be that fast first order methods have been dominant anyway. And so I'd just love to hear your opinion on all of these things.
So for continuous samplers, there's been a lot of great work. I'm a little bit out of touch with them now, with whatever state of the art continuous sampler there is, but something very similar is possible inside discrete diffusion samplers. So it's a different problem, but people have formalized discrete diffusion in a variety of ways, but there is some kind of flow matching or continuous time markup chain papers where they analyze it kind of similar to a ODE, SDE style stuff that like some of these samplers that you mentioned are based on. And I think there's even like the notions of higher order samplers, like second order, third order for samplers with discrete diffusion, but I'm not 100% familiar with that. But I think so there is similar work, and it comes from a similar point of view, from like a similar theory point of view. It ends up being a little bit different because you're dealing with discrete data and stuff, but they're similar. I do think that samplers in general is kind of one area that hasn't had a huge amount of attention for discrete diffusion, and it would be good to get a lot more work there. And like at a high level, without even considering the theory of discrete diffusion being analyzed like a continuous time markup chain, you can just think of like at the top, when you're trying to generate samples from a discrete diffusion model, you like, let's say you've got a block length, what we call a canvas of 256 tokens. And at the top of the transformer, you're going to have a probability distribution over your vocab for each position. And those are totally factorized. So they're not joint. It's not a joint distribution, which is what you'd like to sample from. They're just factorized marginals. And so if you sample from that naively, you can get problems of like stuttering and things like that, where the model isn't quite sure where to put the word the or something like that, and ends up putting two thes in a row or something like that, or it doesn't quite know what mode the tokens are going to pick, because once you get into the each being a totally marginal probability distribution, they can't coordinate at that stage. And so there's a bunch of work going in to like on my team on trying to like sample efficiently from that, or like do some sampler distillation to make it easier to sample efficiently. But I think just there's so much more work that we could do. I think there's like a lot that if we could just, sample from that marginal more efficiently, or somehow figure out how to get them to coordinate better or whatever, then that could be a really big unlock, because we spend some amount of the denoising steps, some amount of the forward time that we spend on the neural network is really just coordinating the tokens, like trying to make sure that they agree on what they want to say. And if we could have that by a much better sampler, like have that the number of forward passes we do, that would be a huge unlock and make things even faster and cheaper. So I probably would fully close the throughput gap, because I think the throughput gap is less than a factor of 2. So if someone had, like, one of the reasons we open weight released Diffusion Gemma was in order to get people to work on that, because now you have like a basically a state of the art text diffusion model that can fit in a H100 and just go and like figure out the best way to sample from this, right? Or figure out new sampler distillation techniques or something like that. And if there's a big breakthrough there, I mean, that would help the entire community. That'd be amazing.
And how much so diffusion models started from vision, like it has like very strong theoretical background, right? Like intuition from theoretical background. How much you think it's important, today that like we are talking about discrete diffusion, that it's not clear, like I know there are several attempts, like to build a theory for also discrete models, but how much is important? Do you think this is something that like we can, there is.
Yeah, it's a good question. It's hard. Like, I think understanding these models better, so building on the theory, would be very useful. And there is really good theory papers for discrete diffusion. Maybe it's definitely not quite as developed or as well understood as continuous diffusion. And there is definitely a bigger gap between theory and practice for discrete diffusion than there is for continuous diffusion, where it turns out that for the most part, the theory and the practice line up reasonably well. Whereas in discrete diffusion, you kind of have a bunch of different things that aren't quite, ideal because you want to sample many tokens at a time and things like that. And like a lot of the theory papers don't allow that. I think you can build, one view that a lot of people take from a more deep learning perspective is that discrete diffusion models are basically BERT, the BERT language model, which is a mask fill in, kind of like you mask out some tokens and you fill them in. You learn to replace the mask tokens. It's kind of BERT with like multiple varying noise levels and then sampled from. So it's like kind of from, if you imagine what's the ancestry of text diffusion, you can draw a straight line to BERT and that entire line of work, because it really is building on that to say, well, if you can fill in the missing tokens from this mask sequence that you're trained on, then you could do it from every type of mask sequence, and then you could sample from the model. And so a lot of practitioners, I think, don't necessarily need to know the theory to have an impact. But I think probably in order to make more progress and to really close any remaining gaps and to go way beyond autoregressive models, because I think text diffusion models have a higher intelligence ceiling. If we can solve these problems, will require some innovation that may need some kind of more theoretical breakthroughs.
So these diffusion models, the theoretical breakthroughs, like, do you think they're being worked on? Like, do you think the community working on this is large enough? Or I ask just because I see ebbs and flows in the community, and I can tell you there seems to be more papers on world models these days than on diffusion language models, for example.
Yeah. I mean, I think it's a really hot area. Like, there's a lot of stuff coming out, lots of great papers, loads of great PhD students, loads of great professors working on this. I think like there was just ICML Best Paper Award. One of them went to a text diffusion model. I'd love to see more. One of the reasons we open weights released Diffusion Gemma was to try to like give the community a really good like state of the art fusion model that people could play with, they could build on, that they could learn from, that they build some intuition in kind of in the same way the Llama model from Facebook from 3 years ago as an open weights model really spurred on a lot of great research from academics and so on who couldn't afford to pre-train the entire thing from scratch. But once they got a model in their hands, they were able to do a lot with it. One of the big motivations for us to release this was to try to do something similar for the people who work on text fusion, and also like people can fine tune it for their own application. And I've seen there's been some really cool applications already for that. But I think it would be great to see more research in this area. I think I'm confident that enough people are working on it, and it is making pretty rapid progress. I think if you think about diffusion models, the original diffusion model paper with like Joshua Sol-Dickstein from, I think it was 2015 or something like that. That's a long time, like 11 years. Whereas discrete diffusion I'm not sure exactly what the first discrete diffusion paper was, but maybe the early 2020s. Emil had an argmax flow paper in 2021. The D3PM paper, I think, was also 2021 or maybe around there anyway. So, there's been several years. We're lagging by several years. So I think there's like some catch up. And I think right now is actually a great time to get involved, like for, PhD students, because text diffusion is a much less explored area than autoregressive models, and the frontier labs are doing much less on it, and so there's more scope to have an impact. Whereas kind of if you're working on autoregressive language models, you don't have the compute to compete with the massive labs. There's so much secret sauce locked up in these huge frontier labs. But I think it's much more open, first of all, in text fusion, and there's way more to do. So I think like it is an exciting area, and I think it would be, if I was a PhD student now, it would be one area I'd seriously consider investing in, because you could have an impact, have a really big impact, and there's still a lot to do.
And what do you think are the main bottlenecks? It looks at like all of the pipelines, right? Like the data, the like pre-train, mid-train, post-train, all these are really highly optimized for autoregressive models. Do you think they're also like aligned with diffusion models, or do you think like where are the things that we actually need to change in order to get better performance?
Yeah. So I think there is a lot of hypertuning for autoregressive models. So, architectural decisions that people are familiar with would need to be changed. Scaling laws need to be changed. RL algorithms and RL infrastructure would have to be different. Sampler distillation is a whole new thing that autoregressive models don't do, that we'd have to do from scratch. I think things like data and so on are roughly the same, so that probably wouldn't need to change much. But they're like, just comparing what we did with like Gemini internally to Google. Every part of the infrastructure is so hyper optimized for autoregressive models. It's quite hard to actually do something a bit like text fusion, which is quite different. It requires different design choices, and we kind of mostly just picked up the design choices that they did for their thing. And there's some regret that we incur for that, I think. And like if someone really did just hyper optimize for text diffusion, you'd end up with a different like trade-offs and different models, different hypers, and you'd probably have an overall much better model. I think like some of the more interesting areas for research right now is, I already mentioned like better samplers, better ways to sample from that marginal, or just like train it so you don't need to do anything clever. I think continuous diffusion for text is another really exciting area where, people did do it a few years ago. It kind of fell out of fashion. Everyone was doing discrete diffusion, including us, from like 2023. And that really pushed the quality a lot for diffusion models for text. But now I think there's a chance to maybe take a step back and say, actually, if we can get continuous diffusion to work for text in some way, then, in a latent space or something like that we learn, and there's some really good papers coming out in this direction, then we could unlock using all the really sophisticated work that's been done for the continuous diffusion, which is like several years more advanced and has way better, noise schedules, samplers, distillation, just because it's been going for longer and there's been more investment in it. So, I think anything that would like improve the throughput, improve the latency, improve the quality, tricks in training to just make it, overall higher quality, any of these could have a really big impact.
Do quantization and pruning methods kind of map from language models to diffusion models. And, it seems like there's this tendency that the bigger the model is in terms of parameter count, that you can get away with increasing amounts of quantization, like to lower precisions, while preserving more of the quality. Is that the case also with larger diffusion models?
Yeah. So pruning, I don't think I've ever looked at that side. I don't know. But quantization, we find that at least it's as easy to quantize a text diffusion model than an autoregressive model. And I think if everything was working right, it would actually be better to quantize a text diffusion model because of this like iterative refinement and error correction property that it has. So if it does make a mistake, somehow something's gone wrong and it's sampled a bad token for whatever property, it could be for whatever reason, it could be because of the quantization. It has a chance to look at that error and correct it. So I think in principle, right now I think quantization is basically neutral between the two, and they kind of roughly have the same, performance after quantization. But I think if things were done right, it should be even easier to quantize a text diffusion model.
And what about hardware? Do you think is it possible to optimize the hardware for text diffusion?
Yeah. So I think, text diffusion, it's really well suited to modern accelerators. It's one of the reasons that I think it's got a real potential to really accelerate in the future, because GPUs and TPUs, they have a ton of flops in their, whatever the MXU, the matrix multiplication unit, whatever that's called for a GPU. They have this tight, HBM bandwidth channel where you want to, transfer the weights and the activations in the KV cache or whatever from HBM across this tight channel into the MXU and do the flops. And the amount of flops you require versus the bandwidth you require for text diffusion is different than for autoregressive models. So they can make much better use of the GPU, because for every time they transfer the weights, they do a way more flops, and they only have to transfer all the weights, 10 times when they're generating 256 tokens instead of 256 times when they're generating 256 tokens like an autoregressive model does. And if you're memory bound, because that bandwidth is so tight, then that's why autoregressive models are slower, because they have to do more memory transfers. And now we're popping these companies like Cerebras and Grok and so on, who are popping up. They're building dedicated hardware for inference, basically, in order to try to get autoregressive models to be like faster and easier to serve. But I think it's basically a hardware solution for an algorithmic problem. And probably the longer term solution is to use something like text diffusion, where you can just make use of all those flops that are on a GPU much easier than an autoregressive model, and then just solve the problem algorithmically by making text diffusion way better than autoregressive models or whatever, and then be able to have better inference that way, and rely on generic hardware instead of relying on custom hardware like some of these hardware startups are doing. So I'm pretty bullish. Like, there is some co-design potential for both of these technologies with hardware, but it's easier and cheaper, and overall in the future, like looking forward, just it's going to be a lot more flops on future generations of GPUs and TPUs, and then that it is to put, like, it's harder and more expensive to put more bandwidth on, and it's like physically harder to put more bandwidth on. And so going forward, I think there's going to be more and more flops, and it's easier to put flops on. So text diffusion is well suited to that because it can make use of the flops. Whereas autoregressive models, either it's going to be custom hardware, there's going to be tricks to try to make use of the flops without like when it's saturating the bandwidth. Yeah, so I think hardware is a big thing. Like, for both models, it's a big open question. I'm overall bullish on the direction of travel for GPUs and TPUs with the amount of flops and bandwidth they're able to put on. That it's going to be more and more likely, more and more favorable for text diffusion going forward.
What about government regulation, right? We've already seen, Fable Mythos and then GPT 5.6 and others kind of have to go through strict government regulation, already having their capabilities neutered on cybersecurity and biology tasks. Chinese governments talking about kind of stopping the open source renaissance or golden age that's going on, from there, and forcing labs to close source everything. Do you think that this is a real risk of happening soon? And if so, do you think it will affect diffusion language models?
God, I hope it doesn't happen. I hope everyone has access to the best quality models, obviously in a safe way. And I hope open source doesn't go away. That would be terrible for a lot of people who, like, a lot of startups are using like open weights models. right now, text diffusion, the models are much smaller and they just don't have the same dangerous capabilities than that autoregressive models do, at least currently. If that changes in the future, if we do scale up to a massive model or just some big breakthrough and like people are able to push the boundaries of smaller models way further than autoregressive models, then yeah, I don't see why they wouldn't be regulated the same way. But hopefully that doesn't happen.
And so, what do you think about AGI? Like, it looks that at least in the Silicon Valley, the main narrative now is that AGI is around the corner, and like basically everyone will lose their job in like 6 months, and
Yeah.
we need to get ready. What do you think?
Yeah. I think AGI is coming. I think if you kind of, modulo things like hardware being hard, like robotics being a bottleneck for progress in embodied intelligence, if you just think of Mythos or whatever as being further closer and closer to AGI in a box that doesn't have to be embodied, but can do everything that like you can do in software. So anything got to do with text, including science and math and writing code and running experiments and so on, or even proposing experiments for a wet lab or something like that, then I think it's coming. It's probably coming pretty soon. By that definition, probably coming next few years would be my guess if the trajectories continue in this direction. Are people going to lose their jobs? I mean, there probably will be some displacement. I mean, this is not my area at all, so like I'm probably going to say something really stupid here, but I imagine that there'll be some displacement with some jobs will be lost. But I think it will unlock hopefully it'll unlock, if we do it safely and correctly and all that, it will unlock such an amazing era of like progress and prosperity and, curing diseases and giving everyone access to, high quality, the best tax advisor in the world, the best legal advisor in the world, the best, mathematician and scientist is all available in your pocket, the best psychiatrist or the best marriage counselor or whatever, and they're all in your pocket. That should be a massive prosperity increase for, the world and all the impacts that AI can have in science and mathematics and technology and so on. Are thinking that yes, there probably will be some economic displacement of jobs, but I'm hoping that the benefits of AI and AGI would be just so extreme that it massively outweighs the negatives if we can do it in a safe way. I mean, if everyone has access to a cyber weapon, that would be bad. But if everyone had access to like the best coder in the world who knew not to do cyber attacks on your behalf, then that'd be great.
And what do you think about the argument that, like, yeah, coding agents are great because code is very verifiable, in math, like we almost solve it because everything you can verify it all the way, but the real world is much more messy, like when you involve, like you have humans in the loop and like some decisions that you need to make, and the real world, right? Of course, the physical world. Then LLM like are much more like they have a lot of difficulties there, and like the progress there will be much slower.
Yeah.
What
I
do you
mean,
think about it?
I think that's absolutely correct. I mean, I don't think the second we get AGI will, solve all the world's problems. There'll be bottlenecks or like, slowdowns that are not related to having more intelligence in a data center, but related to just like real world, requirements on running experiments and, actually building things and so on. And like just real physical limitations will slow us down. But my guess is just if it really is AGI, it will propose really good experiments to run, and those will be better than the humans could have proposed. And humans will run the experiments and come back with like the results, and the AI will be iterating on that and figuring out next things to run, and we'll make much quicker progress than we would have without it, even if it is bottlenecked by things that are kind of out of its control.
And what do you think? Like, so last week we talked with Daphne Koller, and she's
Definitely, yeah.
yeah, yeah, she's great.
She's great. She's great. Yeah.
Yeah, and she has a company for drug discovery, and basically she claimed that like, yeah, the running and discovering new molecules it's the easy part that we can automate almost fully.
Mm.
But the hard part is actually like to run these experiments and to try it right on like humans, for example. Also, we talked with Max Welling that basically they're doing the same thing, right? Like when you try to automate experiments and wet labs, and when you try to deal with the real world, like the main bottlenecks are not there, or not like in running and writing your code faster, or like thinking about different
Yeah.
I don't know, some like new moleculars or something like that, but like to actually run it, and you can speed up like the real world.
Yeah.
Well, what do you
Yeah.
think about that?
I mean, it sounds, I mean, I believe Daphne when she says that. I mean, she's done great work. So, I mean, I think that's exactly right. But, you know, we will be bottlenecked by things like the wet lab and how long it takes to run experiments. It is great to be able to automate that part though, right? If maybe it is the easy part, just like coming up with candidate molecules to test or whatever, Daphne was saying. But it is great to, you know, have a superhuman agent that can do that on our behalf. So at least that part is solved. And if it really is able to come up with much better candidate molecules, then, you know, if you imagine how many successful, like drugs go from candidate molecule, let's say that rate is 5% or something from candidate molecules to actually therapeutic drug on the market. Maybe that goes from 5% to 20% or 50% or whatever. And that would be a massive breakthrough. And that would be massively accelerating drug discovery and, you know, compress 10 years down into 1 year or something like that. And that'd be huge. So, you know, I think there are these bottlenecks that are inevitable, like Daphne mentioned, like just, yeah, it takes time to run these experiments and to like see the effect of whatever molecule you're developing. And it's going to be the same in many areas like robotics and things like that. They're just going to be physical bottlenecks that the AI can't help with, but you'd think that the inputs would be so much stronger that maybe it still accelerates us a lot. That's my hope anyway.
And do you think that these diffusion models have a part to play in so-called recursive self-improvement, right? Which is the component, right, that's happening supposedly now with Claude Code helping Claude, make Claude Code.
Right. Yeah, I mean, I think that could happen for two reasons. Like one concrete reason today is that they're just much faster. So if the recursive self-improvement requires writing a lot of code and, you know, agentic coding can output like literally hundreds of thousands of tokens. If you can do that 10 times faster, then you have 10 times faster turnaround on every call to your recursive self-improver. And the other reason I think there is a possibility that it could is that even though it's not the case today, I think diffusion is a more powerful way in principle to generate text if we got it right, because it can do bidirectional reasoning, this self-correcting and this like iterative process that if that could really pay dividends, then maybe it's just a much higher intelligence ceiling than autoregressive models for the same model size or something like that. And so those two combined, it could be the case that in a couple of years, that the text diffusion models are how we do recursive self-improvement. Yeah.
I notice, that there's always this history of technologies that anticipate a technology, or even, gamification. So I'll give an example here. In generative AI in general, there was a series of games called Scribblenauts, which had been around for a long time, where you could literally, in natural language, describe objects that you wanted to appear in the world, like any object, and use them to help your character solve tasks. Now, they did this based on a pretty intelligent system of objects and properties and, individual mapping, and obviously lots of limitations to this, given that it was way before LLMs. But there's Scribblenauts, and then in the case of BERT, and bidirectional reasoning models, I mean, there's literal Mad Libs, right? Like I see those to this day, and I always think about how you could just synthetically generate 100 billion Mad Libs books using, the technologies NLP folks have perfected. So I'm just curious about, like, do you see these other kinds of like anticipation of technology where, it goes kind of under the radar for a while and then it gets really huge suddenly in this space?
Wow. Yeah. That's a very interesting question. I had not thought about that at all. Wow. It's hard for me to really answer that. I don't really know. I guess so. I mean, I guess if you say BERT, like if Mad Libs kind of anticipated BERT and BERT kind of anticipated modern text diffusion, then maybe I can see the the ancestral line from MATLABs to BERT to text diffusion, and maybe there's some child technology that's going to come next, and that'd be great. Maybe it goes back to MATLABs and the circle completes. Yeah, I mean, I like to think of like, transistors were preceded by vacuum tubes, and people invested a lot in vacuum tubes, and they were the state of the art for, computation at the time. They were huge, and they were expensive to make and very delicate, and you could only fit a couple of hundred of them. You couldn't miniaturize them. And computation was going to be done that way until somebody developed transistors, and then they were way better at some point. Like, it took a while for people to switch over and to realize. But then once the investment went into transistors, obviously, then we had the full computer revolution and so on. So maybe some of these technologies are like that progression from, vacuum tubes to something that's ultimately going to be stronger, but we don't know how to make it like just as strong as it's going to be just yet. And there's going to be more time to be required to iron out the details here. But yeah, very interesting question. I'm sorry, that probably wasn't a very good answer, but
So I have a question. So like a lot of people say we are in the engineering area, right? Like we don't do any science anymore, and what we are doing is just like try to optimize very small things in order to make it like, I don't know, 0.1% better on the benchmark. Do you buy that? Does it bother you?
So I think there's a lot of science that goes into doing careful autoregressive language modeling. I mean, I think it's empirical science, but it's science, and it's very, very careful because of the sheer cost of running a big training run. And some people spend a huge amount of time and effort doing very, very, very careful scientific experiments and ablations, which really are science on these models, which are an empirical science. I got like a real physical science of an emerging phenomenon of this. It's weird, but it's like in the computer, but it's still just like observing the physical properties of something that's outside the computer. You really do have to like look at what's happening and then make decisions based on that. But I do get your point though. And one of the reasons I was attracted to working on diffusion in the first place was because of the beautiful theory and the elegant mathematics that went into like the original diffusion papers, like the original ones doing score matching and SDE equivalence, and all the really cool theory work that's gone in that direction, and that really has a practical impact, so that you could use this theory to generate beautiful images. And there is still very elegant theory in discrete diffusion as well, and like I think there's more to be done there in a way that like I don't know if autoregressive models will have the same like underlying elegant mathematics. Maybe, but I don't necessarily see that coming. So, yeah, I think, it is a type of science. It's not really theory, but yeah, I'd love to see more of it. And it would be great if there was if it could be like continuous diffusion, where the scientific or the mathematical impacts or breakthroughs had a real practical impact. I'd love to see, and I think people are working on this, but I haven't seen something actually really have impact. So I'd love to see like a theoretical analysis really showing something about the capacity and the power of transformers. Like, why are they so good? People have done a bunch of kind of work in this direction, but I haven't seen anything super convincing. And if someone was really able to analyze that and really show, oh, look, this is this new mathematical theory that describes how transformers are so powerful, because they've replaced, everything. And then suddenly we understood it. And maybe from that theory, maybe we could build better transformers because we understood it a bit better, or something like that, better architectures. That'd be amazing if we had that.
Well, so what's your opinion on things like state space models with Mamba and et cetera?
Yeah, they're super cool. I love that work. I don't know if it's had a huge impact on the frontier models yet, from what I gather. It would be good to understand why, but maybe just something's missing there, and in 6 months' time there'll be a big breakthrough and everyone will be using SSMs. But
I think like in recent models, right, at least like the open source one, on some of the layers they are doing they're doing kind of like linear attentions that really similar to these state models, right? State space models, and they combine between like full attention and linear attention and state space models. So it's kind of at least in the open source models.
I've seen some interleaving work. Yeah, maybe that is where things will go, like interleaving the state space model layers with like say 5 regular attention layers or something like that. Yeah, maybe that is the future. They are cool and elegant, so it'd be great to see if that got more traction. Yeah.
So what is the most overhyped idea in AI right now? And what is the most underhyped idea, in your opinion?
The most overhyped and underhyped ideas. Wow, you really put me on the spot here. Well,
You don't have to answer if you don't want to.
no, I'm not worried about offending anybody. I need to actually think of it. I need to actually come up with it. Like, what is the most overhyped and underhyped? Maybe I think some of the, this probably will offend people, but maybe some of the video and image stuff, I think maybe a bit overhyped, because I think it's overhyped a little bit because, like when you see an amazing video out of one of these models, it's so visual and so gripping and so obviously amazing that how on earth did a neural network produce this, that it is mind blowing and people are like, whoa, and they're like, this is incredible. But that can lead to overhyping because I don't know yet if they've had a huge impact on, products or technologies in the same way LLMs have, in the same way Claude and GPT and Gemini have for actually writing code and having useful outputs. But I think there's probably more to do there, but they're so gripping. And then people invest a huge amount into them, like in terms of compute, resources, money, people. That is, maybe it's a bit overhyped because at least right now, I don't see a massive way for that technology to have a huge impact. I guess people are invested in world models. And that's obviously going to use these technologies as an underlying part of that component of that technology. And then world models will lead into better AI and better robotics and stuff. So maybe it'll achieve the hype that it kind of has right now. But I think when you see a 15-second video of some state-of-the-art image video model and people are like, oh, amazing. And then they send it to each other, they send it to their friends. Look at this amazing video. But then they forget about it. Like, this doesn't have any stickiness. And the cost of training those models is unbelievable. It rivals training a frontier level LLM, and it has almost no sticking power. Like, there isn't right now a use case for that for people in their day to day. But I think there will be probably. The world models maybe is that direction. I think maybe they are overhyped and underhyped. Maybe this is a bit trite at this point, but maybe reinforcement learning still. I know reinforcement learning has had its renaissance and everyone does RL now and everyone says that RL is what makes Claude Code work or whatever, agentic code, and the same for all the other frontier labs. I still think it's underhyped. I still think, it's so powerful a technology. We've barely begun to scratch the surface. And if you think about what will we need to really reach AGI, it can't be more pre-training or more SFT, right? Because that puts a limit of human capability onto the model. Like if you pre-train the entire internet, the model is as good as the entire internet. You have SFT on maybe some human generated coding problems or whatever. That's the limit. And they did that for AlphaGo. Like for AlphaGo, they trained the initial version, trained on all these like expert matches. And it was a very good player. It was a competent, expert human level player that would rival a top, say, 20 code player in the world. But they threw all that away and just RL'd from scratch, like no training data for AlphaZero. And that was way better, like miles beyond human capability. Not like 1 or 2 stones, which are these like penalties you can give to a much stronger player. You can give the opponent stones in order to compensate for the ELO difference. It was not just 1 or 2 stones different. It was like something like 9 or 10 stones different. The difference in the very, very best humans who had spent their entire lives learning Go from a young age to becoming like one of the best in the world to a neural network that spent 5 days doing RL from scratch was astonishing. And it's going to have to be the case for LLMs to reach AGI that at some point we'll reach the limit of pre-training data. Just from a data point of view, like not from a neural network architecture point of view, just from a data point of view. And to really become superhuman, it's going to be a ton of RL. And I think, I imagine that in the future, there's going to be a lot more reinforcement learning of these models than SFT pre-training. So I think even though it is super hyped, reinforcement learning probably still is underhyped for, getting to AGI.
Do you think that diffusion models does reinforcement learning operate differently on them than autoregressive models?
Yeah, it's a good question. We did have to come up with some new algorithms, some new techniques just to compensate for the fact that you don't have the likelihoods that you have in an autoregressive model. Like you don't have the probability of this token being generated. So we had to come up with some new algorithms there. But ultimately they look very similar to what is already done. So I think like rather than think about it as an algorithmic, what's different, I think really it's just the concept of RL. Like you can do RL many, many different ways, even for autoregressive models. If you get the recipe right, you give a right reward function and a right value function or whatever it might be and let it climb. Kind of doesn't matter what the actual algorithm is that much, as long as it kind of makes sense. That you'll see text fusion RL, text fusion autoregressive models will climb.
And do you think there are like some classical real ideas that we can use, right? For example, like the GLM model, right? They just published that they actually like use the critic, like kind of like a PPO style instead of the GRPO. Do you think there are like more ideas that we can revise and use?
But definitely. I mean, RL is a massive field for going on 20 years. And the algorithms that LLMs are using are just so primitive compared to like their super sophisticated ones that are available and analyzed in the literature. Using a critic, like a value function critic, that's the reason it's not happening is because it's hard. So people haven't really been able to work out all the details yet. But I think definitely value functions will play a huge role. I think like I in my previous life before text fusion, I did a lot of reinforcement learning theory on what's called like exploration, which is like the exploration exploitation trade-off, where you try to have an RL agent like explore, as in like take suboptimal actions in order to learn more about the environment that it's in. So, move away from what I think is the most rewarding set of states and actions into kind of novel territory in order to learn more and maybe potentially find a much better reward. So that's kind of exploration at a high level. And there's no exploration, as far as I know, in any RL algorithms that people use in practice. I don't think it's ready for that. Like I think we should get value functions before you try to do any sophisticated exploration techniques. But if we think about what is required to get to superhuman intelligence, it will be required for the model to like actively leave the manifold of the data distribution it was trained on to go off and try to find potentially much more rewarding states by leaving the distribution that it's been trained on and finding something new. So exploration, and maybe it's a simple form of exploration, but something will eventually be required in there in order to really squeeze more performance out of these models and really get them to become superhuman. So I think, there's loads. I mean, that there's been so many great people working in that field for so long, working on either pure theory or like relatively toy problems, like 4-room or even Atari is relatively toy today. And that we're just waiting for that overhang of all that literature and that knowledge to translate into practical algorithms for LLMs. And there's a few things missing. Like people have tried it, obviously, and they haven't translated yet because it's simple things are not working well yet, like the value function critic, like you said. But as soon as that happens, I think like there'll be a massive, takeoff as long as we have the reward functions, because we have so much knowledge from reinforcement learning, all this work that people have done for so long, and it will eventually have the impact that I expect it will on frontier level LLMs. And then I think it should really take off at that point, which is kind of why it's underhyped a little bit as a field, because like we're waiting, there's like so much stuff there that could just be, when we get the details right, could be applied and really take off the, how we do RL for these things. And if we think in the future, we're going to be spending way more flops in RL than in pre-training, then there's a huge possibility of having a massive impact there with new RL techniques, or even RL techniques just taken from the literature.
So 2 years from now, like 5 years from now, how do you see the pipeline, like both in performance and also like the algorithms, like how AI will look like bigger models, smaller models, like?
Yeah, I think the direction of travel is for bigger models. I don't see anything holding that back. I don't think people will. I think scale is still giving so much benefit in predictable ways that we'll just keep scaling these things. And yes, I think we'll have smaller models that are more capable than the smaller models we have now, but I'm sure the frontier is going to increase in size in terms of the many trillions of parameter models that they are now. I just don't see a direction pushing that down for any reason. People make these like connections between like the number of synapses in a brain and the number of parameters. I mean, I don't think it really makes sense, but like people say there's quadrillions or whatever in the brain. There's only trillions, so we still have a long way to go. I don't know if that makes any sense whatsoever, but there are measurable and real gains from just increasing your model. We know that, like still today, like pre-training is not tapped out. Maybe data is more of a question that maybe like you kind of run out of data. Like if you train on everything everyone's ever written, you kind of maybe max out or something like that. But then I think you can still have more, you can use that capacity for RL later. So I still think you'll have bigger, when it generates its own data, where you can still push the models bigger and bigger. So I don't see anything pushing them to make them smaller just yet. So I think scale will keep winning. And what was the second part of that question?
There wasn't like I basically want to ask like what you think, like how the future will look like, in terms of like both like pipelines and performance and like
Right.
architecture.
Yeah, so I think models will probably get bigger. Pipelines, I'm not sure. I guess more. Like I predict probably more overall flops and time will be spent in reinforcement learning, and that's kind of just going to grow as a fraction of the total training flops from where it is today. I think in terms of capabilities, I don't see any limit right now on what these models can do. Every limit that's been proposed has been smashed through eventually. So and hasn't required specialized stuff to do it really. It's just make the model bigger, train on better data, do more RL. And it just solves whatever problem was kind of a sticking point at that point.
And what about like diversity of the models or like the components? Do you think we will see like converge to some I don't know, it may be like autoregressive or diffusion or whatever, but do you think you will see like some like converge to specific type of models, or like different types of models will be quite similar, or like maybe good in different aspects?
I think it's hard to predict. There probably will be some converge. It's hard to know.
Prediction is hard, especially about the future.
Yeah. Yeah. I mean, there is convergence right now. I mean, I think all the frontier labs are using MOE transformers pre-trained on a huge amount of data, and then RL on a bunch of different RL environments. I think that's basically the recipe that everyone's doing, and we're all executing it in different ways and getting slightly different results, but they're only slightly different. Right? And like, these things ebb and flow so much that 6 months things change so quickly. One lab is in the lead and another lab is in the lead. Is it going to stay converged? Hard to know. I mean, I do think probably recursive self-intelligence stuff will start kicking in, where the model starts to be able to improve itself. I think we're seeing signs of that already. And maybe that ends up with more diversity or something like that. And maybe these models start training themselves, or start post-training themselves, or start proposing new architectures themselves. I could definitely see that happening soon. I don't know would that imply a convergence? Maybe, but I do think as well, we'll see a proliferation of LLMs or like AIs, or like pseudo AIs, into many, many aspects of our lives. It won't just be like on your web browser or on your computer working with agentic coding or whatever. I think it'll be on your phone. It'll be like, in your microwave. It'll be whatever. Like it'll be all over the place. And those will be different models, maybe much smaller or something, and maybe communicating with each other in some way. And it won't be just big server-side models. There'll be models all over the place that are performing different functions, would be my guess. And that probably means there's a bit less convergence, because those will be slightly different in different sizes and different trade-offs that they have to make. But yeah, it's hard to know.
Okay, I think we're out of time. Do you have anything else that you want to add?
No, I mean, thanks for having me. This has been great. Yeah, I guess maybe the last thing I'll say would I'd love it if people were able to pick up the Diffusion Gemma model, fine tune it for your use case, or find some new sampler, or just use it as a base for research. I'd love for people to be able to play with it and, have some push the boundaries of what text fusion can do, write a paper, obliterate it, like you were saying, Alan, figure out a way to break the safety guardrails and write a paper about that, so we know exactly what's going on there, or even just do interp work on it. I think we're only at the start of understanding what the diffusion models are doing in terms of what they're actually thinking and what they're capable of. Yeah, so I'd just encourage people to check that out. Download it, play with it, run it on your own machine, put it on a random new piece of hardware that no one has ever run it before, and see if it still runs. And yeah, just see if you can have a contribution to text diffusion and help us push this field forward.
Great message, Brendan. Thank you so much for joining us. It was a pleasure.
Yeah, it's been great. Thanks for having me on, guys.
I learned so much from you. This was a great discussion.
Yeah, I mean, you asked me
Thanks.
some pretty tricky questions that I hadn't ever even thought about before. The connection between Mad Libs and
No.
BERT is really that is a new one for me, and I enjoyed it. I really enjoyed it. It's been a fascinating discussion, and thanks for all the questions. It's been great.
Thank you so much. Thank you.
Cheers, guys. Bye bye.